Hi, welcome back to Lecture 4, titled More Rates of Change, Acceleration. Now, this one is often tricky for students to grasp. It is completely analogous to the rate of change, velocity, and speed that we talked about in Lecture 3. However, this is the rate of change of a rate. And I think that what makes it a lot easier to get initially is if we do a couple of things. Number one, we're going to give velocity its own unit name, just for a temporary placeholder. We'll revert back to the standard way of saying meters per second or miles per hour later on. But for now, I want to call them zips. Right, so let's define one zip to be equal to 1 meter per second. And the acceleration is the rate of change of velocity. So I'm going to write this down. Acceleration is equal to delta V, which is just measure a final velocity, measure an initial velocity, take the difference between them. That's the delta V, the change in the velocity, divided by the time interval over which that occurs. So t sub f minus t sub I, and that will be our acceleration. And so I could say, for example, that I had an acceleration, I measured, let me just draw a velocity versus time curve here, velocity versus time, and let us say that at 1 second we observed a velocity of 1 zip. I'll put a Z for zip. And then at 2 seconds we measured a velocity of 2 zips. So you can see that again we have a nice straight line. That's a constant velocity. Excuse me, it's not a constant velocity, it's a constant acceleration. And so our velocity is increasing linear in time. And how quickly is it doing that? Well, if we take our final velocity, which was 2 zips, and we subtract our initial velocity, which let's say was 0 zips, and divide that by the time interval, delta t, which is 2 seconds minus 0 seconds, then we get 2 minus 0 is 2 zips divided by 2 minus 0 is 2 seconds, which is 1 zip per second. So that's our rate of change, or our acceleration, which means that every second we are attaining 1 more zip than we had before. Now let me just change this. Let's change this from seconds to minutes. This was the second change that I wanted to make, because I think it makes it a little bit easier when we get rid of the zips and we go back to, I'll put MIN for minute, because if I just put M, it would look like meters. Minute, there we go, and here as well. I guess I could have used hours, but that would have been easier. All right, so our time, which we're measuring in minutes, this tells us that we attain 1 more zip every minute. Okay, but I'm going to keep what a zip is as still 1 meter per second. So if I now get rid of the zips, what is my acceleration? Well, 1 zip is 1 meter per second. So I'll still have 1 zip, which is 1 meter per second per minute. Which means that after 2 minutes, I would have attained an additional 2 meters per second. After 3 minutes, I would attain another 3 meters per second. Pretty straightforward. Where people get confused with this is that if I now, instead of using minutes, I use seconds, what happens? Well, there are 60 seconds in a minute, so this would be 1 meter per second divided by 60 seconds, which is, we're just going to write this as 1 over 60. Meters per seconds times 1 over seconds. Well, that's 1 over second squared. And so acceleration in SI units has meters per second squared, and that can be confusing. Another way to say it, you could say 1/60th meters per second per second. That would remind you that the rate of change is a rate of change of a rate itself, which is velocity, which is meters per second. So it's meters per second per second. And that essentially is what acceleration. We can say the same things about average acceleration and instantaneous acceleration that we did when we talked about velocity. All of that ports over directly to acceleration. And I think that's it for acceleration.